Prontissima.
Okay. So let us start this morning session, with the first two lectures by Valentina from Saclay University, with an introduction to many-body localization.
Yes, thank you. So, of course, begin. Well, first of all, good morning, everybody. So I of course, want to thank all the organizers for setting this up, also people that gave the technical support. So I will try to switch between first 10 minutes that will be on slide, and then I will go to the blackboard. Well, thanks for giving me the chance to join this school and also to follow the previous lectures that were interesting. And to the people online, I just want to somehow, so I know that it is a bit hard to interact in this way, but please feel free to speak up. I think I will be able to see the chat as well, so you can write there and I will try to address whatever point you will raise in there. Okay, so the plan of these lectures is somehow to discuss problems which are related to this idea of many-body localization. So many-body localized systems are systems which have a rather peculiar physics of out of equilibrium, and this type of out of equilibrium shows up whenever you have quantum systems and you put some disorder, which, as we will see, we will assume to be sufficiently strong to give rise to this localization phenomenon. And somehow, before getting into the matter here, I just wanted to show you a picture which is extremely simple, but I think it is worth to keep in mind throughout the whole discussion. And the picture starts from here, so let's make some sort of mental experiment. So let's imagine that we are some experimentalists, and we go to some lab of cold atoms, and we are given a system, let's say a condensate, for example. So this is an interacting system, but to first approximation, we can model it as some single particle wave function. And we are told that this system is allowed to move into some, let's say, quasi-one-dimensional geometry, as you see, the tube in there. And as we get into the lab, at time, say, t equal to 0, this condensate is confined by a trap. So we know precisely where it is, so let's say that it is at the origin of this one-dimensional tube. And then what we do is we go there, and at time t equal to 0, we do a quench, so we release the trap. We wait a little bit, and I ask you, so this is very simple, so if we wait sufficiently long time, where do we expect this condensate to be at, let's say, sufficiently long time after the time evolution? And now, of course, if I tell you nothing else, so just that there was the trap and we get rid of the trap, then what you would naturally expect is that this condensate will evolve with its Schrödinger evolution. It will start moving, it will start spreading, and after a sufficiently long time, I expect it to be, or the density, if you want, to be more or less spread throughout this one-dimensional tube. So in particular, I expect that there will be some probability to find these degrees of freedom more or less everywhere in my one-dimensional tube. So also at the boundary where I am quite far with respect to the position where I put this particle at time t equal to 0. And this is indeed what happens if there is nothing else in the system. But of course, this is not what happens if I tell you something else, namely that on top of this one-dimensional tube, I also put some potential that is very erratic, so that looks very homogeneous in space, and therefore which I can think of as being modeled with some sort of random variables that I throw independently in each region of this tube. So in that case, if we have a random potential, the picture that we will see at sufficiently long time after this releasing of the trap is rather the one that you see in the second tube. So you see that we have a wave function that in some sense looks very similar to the one that we had at time t equal to 0. So our condensate, yes, it's spread it a little bit, but the amplitude to find it somewhere is essentially large only in the vicinity of the point where we put it at time t equal to 0. And then it decays very fast, so the probability to find this degree of freedom at quite large distances, so let's say at the boundary of this tube, is very small, as you see in the picture. And you can actually quantify how small this is. So what you will find is that typically the profile is exponentially decaying. And this is what you see in the picture on the right. So you have three curves in there. The black curve, which is the one that is a little bit more noisy, is the density. So this comes from, let's say, the experimental data. And you see 2 feet. So this is a log scale in the y-axis. So the red curve that looks straight is an exponential fit, which, as you see, works pretty well with the data that you have. And then you also have a Gaussian fit, that is the parabola that is good, let's say, around the origin, but it becomes less good if you go to the tails. Okay, so this is a very simple picture, and it is perhaps the simplest example of what we are going to discuss in here. So I say simplest because this is not yet many-body localization in the sense that you have only one particle. So this is what people call Anderson localization. It is a single particle problem. But it already shows some of the features that we will encounter in MBL. So the first one is the fact that you have these peculiar exponential tails. So this will show up very often throughout the discussion. This is really a hallmark, I would say, of Quench disorder in here. And there is another thing that I would like to stress. So there is another way to look at this picture. That is what I wrote at the bottom. So what you can say is that if I only gave you, let's say, the picture of the second tube, so the time-evolved wave function at much later time, you are more or less able to guess where was your particle at time t equal to 0. So you can guess that before the quench, before releasing the trap, your condensate was more or less localized around the center of the tube and not at the boundaries, for example. So this brings up a little bit this idea of memory, which is preserved in your system and which is preserved locally in space. So you look at the system at large time and you are able to reconstruct what was your initial condition at much earlier during your time evolution. Okay, so let's keep in mind this picture in here. Now, I told you that this is a mental experiment, but actually, if we came here to Florence about 15 years ago or so, we could actually see this experiment being realized. So this that I'm showing on the right are actually data that come from an experiment with cold atoms, which was made at Lens, so the cold atom lab we have here in Florence. So this is the group of Inguscio, Modugno, and collaborators. And since I come from Paris, I should also stress that simultaneously there was another experiment very similar to this one, which was made in the south of Paris in the group of Alain Aspect. So both experiments realized this type of quench protocol. They both found this, let's say, long time limit with exponential tails. There are slight differences in the two experiments in the way this random potential is realized, but apart from that, the phenomenology is the same and the results are very consistent. Okay, so let's say I will just wanted to show you this in order to have the simplest possible example of what you see realistically in the lab. And now what we are going to do is somehow to start from this picture and try to discuss more in detail what happens when you add, for example, more particles to your system and what happens when you have interactions between these particles and how does localization show up in that framework, and this is what is known as many-body localization. So let me just flash what is the plan for these 6 hours that we have. So I thought about splitting this in 2 parts. The first part will be a bit more descriptive, so I would like to give you an idea of what is the phenomenology that emerges in these systems, both from experiments, but also from theoretical arguments that you find in the literature, and also from numerics. So a lot of results that you get in this field actually come from numerical simulations, as we will see. And this corresponds to the first part. So this is basically what we are discussing today. So the first question that you want to ask is, of course, what does it mean to be many-body localized? So I said that you are out of equilibrium, but you know that there are many ways to be out of equilibrium, and each one has its own specificities. So we have to understand what is so special about MBL. And of course, to understand this, it makes sense to compare with some other systems which are out of equilibrium. So I will bring up comparisons with, for example, integrable systems that I will call clean integrable systems, or better answers like integrable system, to stress that there is no disorder in that case. And also with glasses, which are systems where you do have Quench disorder, like in here, but you have a type of out of equilibrium which is slightly different, as we will see. Now, once you try to address this question here, of course, there is another question that emerges naturally, that is, well, but what would we expect if the system equilibrated instead? So we have a peculiar framework in here, which is that of unitary dynamics. So it makes sense to ask, what would equilibration mean in here? And this is a question that is very broad. So I think many of you already thought about this, in particular if you work on integrability. So I will try to go a little bit fast in here. I just want to give a few definitions, and also to stress when you do numerics, how you probe out of equilibrium for MBI systems. So what are the diagnostics that you look at in numerical simulations? And then we will go more into localization itself. So I think there is a natural question that comes up in here, which is, what is the role of disorder? So why is the physics special if you add disorder? What is the mechanism which is behind this localization? So I will sketch the idea behind this. So this will allow me to bring up a concept which appeared already in some previous lectures, which is the concept of resonances that we will discuss much more in the second part. Then I will make a bit of a jump, and I will tell you how do people nowadays understand many-body localization in some sort of unifying framework. So how can you derive all of the phenomenology that we will discuss, starting from some, let's say, simpler assumptions. And this will have a lot of connections to integrability on one hand, but also to quasi-particles and Fermi liquid in some sense, so something that was discussed previously by Sachdev in one of the lectures last week. And then comes the last question that actually should come first, because it is a bit the motivation for looking at these systems, but I think it's worth to first understand what we are talking about, because this helps to understand why people think that these systems are potentially interesting, and it is worth to understand what is going on in here. Okay, so I think this will be the first two lectures, and then in the second part, so this is more about calculations, so I'd like to give a flavor of what are the analytical arguments in favor of the existence of this localized phase, and also the stability of this localized phase. And we will start by going back to a work which is, you would say, rather old by now. So this is the work of Anderson of 1958, but I think that is really a good starting point, because most of the intuition that was developed later on when discussing MBL actually comes from that paper that gave birth to the whole field. So I think it's good to understand what is the line of reasoning of Anderson, and then if we have enough time, I will tell you how to generalize this to, to systems with particles and interactions. Okay, just one comment before starting is that I will not mention all the references when writing at the blackboard, but you find in this folder some, let's say, extra files where I put all of the references. So if you're interested, you can go in there. I hope nobody will be offended by the fact that I don't mention names in here, but they are all listed there. And you also find some simple exercises if you want to play around with the concepts that we will discuss in here. Okay, so this is the plan. Now I will, as I said, switch to Blackboard, but before, so to start with question one, I tried to come up with some sort of definition of many-body localized systems, which is very wordy, so I put it on the slide, and then we will discuss it in more detail at the Blackboard. And so the definition is as follows. So I would say that these many-body localized systems are in general systems that are thermodynamically large. So you think about having a volume which goes to infinity and many particles and a finite density of particles. So you are in the framework of statistical physics, essentially. Your degrees of freedom are quantum, so if you're interested in magnets, you think of them as spins. If you want to do experiments, these are called atoms. If you are interested in quantum information, think of them as qubits. Electrons, if you want to understand transport in materials, and so on and so forth. And they are subject to this potential that, as I said, is very disordered, so that you indeed model introducing quench randomness. And they evolve with their quantum unitary dynamics. And the claim, as I said, is that under this quantum unitary dynamics, these systems remain permanently and robustly out of equilibrium in a way that I will describe. And there is a reason why you are out of equilibrium in here, and the reason is that the transport of your degrees of freedom, and therefore of the global conserved quantities that you have in your system, is strongly suppressed because you have the disorder. And so the type of dynamics that you have as a consequence of this is what people call a dynamics characterized by the fact that you have some dephasing, but you do not have dissipations. So this is a lot of keywords that I threw in there, and now what I think I will do in these 2 hours is to go through this definition and try to give more details to explain what I mean in each of these lines. And I'd like to start by the ingredients that you see in here. So these are ingredients that you find in general in all of these models, toy models, that display many-body localization, and they are essentially 3. So you have interactions which are local in space, you have this quench randomness, and you have unitary dynamics. So let me now give you some more details on this, and let me switch to the blackboard. So let's see if I get this right. Okay, so I think unless there are already questions. Okay, no. Okay, perfect. So question 1 is, what does out of equilibrium mean in MBL? And let me start by summarizing the ingredients. And please let me know if I should write bigger in here. So the first ingredient, as you saw, is the fact that your dynamics is unitary. So what the framework that you're thinking of is the one in which you start at time 0 from some initial condition, which is a pure state. So not a thermal mixture, but really a vector in your Hilbert space. And this pure state evolves with your unitary operator. And throughout this discussion, I will consider the case in which your Hamiltonian is time independent, so that we have at least one conserved quantity in here, which is the energy of your system. And so in this case, the unitary operator is just the usual e to the minus ith. So you can discuss many-body localization also for systems which are driven, in particular periodically driven. And if you have questions, we can comment on that. But for the moment, let me stick to this energy-conserving dynamics. And of course, you can also describe the state of your system at any time, introducing a density matrix, which will be just a projector onto your state at any later time. Okay, so this is a dynamics which is a bit peculiar in the sense that it preserves several things, as you know. So it preserves or conserves the total energy. So the expectation value of your Hamiltonian at time 0 is the same expectation value that you have at any later time, because the Hamiltonian commutes with your evolution operator. It also preserves the norm of your operator. So the fact that you have a pure state remains true at any later time. So what this means is that, for example, the trace of your density matrix square is always equal to 1 at any later time. And in some sense, it preserves memory of your initial condition. And the reason for this is that you have a dynamics which is invertible. I mean, you can invert your time evolution. So this means that whatever information you encode in this initial state, you know that it has to be there at any later time, because from the time evolved state, you should be able to go back uniquely by applying your unitary operator to your initial condition. So there is a one-to-one correspondence, which means that you have some memory which is encoded and preserved by your dynamics. So this is very different from other types of dynamics. So in particular, you're isolated, you have no bath. So you have no Langevin dynamics. That is what you usually look at when you think about glasses, for example. So in that case, you assume that your system is coupled to some bunch of degrees of freedom that you can model as a thermal bath, and so you have a well-defined temperature in there. So here, in principle, this is not the case. And as I said, there is no driving, even though you can extend this notion of MBL to systems which are driven. Okay. So now let me go directly here. So in classical language, you would call this Hamiltonian dynamics, which means that everything about your time evolution is encoded in this Hamiltonian operator. And this Hamiltonian operator has some features. So the first one is that you have some local fields that are very inhomogeneous. And that, therefore, as I said, you model with this Quench randomness. So let's write down an example of such an Hamiltonian. So this is the so-called Anderson Hamiltonian. And let me consider a model on a lattice, so in discrete, in arbitrary dimension. And this Hamiltonian will have, in general, two terms. So the first one is the potential term, where I sum over all the sides of my lattice. I call the lattice lambda. This inhomogeneous fields, so I put a constant in front, and then I put these local variables. This is, of course, A, times a number operator at the site A. And then I have, in general, some kinetic energy. So there is a coupling, the hopping amplitude. And then I sum over all sites which are nearest neighbors in this lattice, something like C dag A, C B plus C dag B, C A. Okay, so this is the potential that I will call H0. And this is where you put your disorder. So this epsilon A are, you have one of these fields for each side of your lattice, and this, you take them to be independent, identically distributed random variables with some distribution of your choice. So let me call it P epsilon. That, so here I'm factoring out the scale of the distribution, so this will be, let's say, normalized in such a way that the width of the distribution is of order 1, so you can choose a Gaussian, you can choose a uniform distribution. Actually, this uniform distribution that people call box distribution is what is mostly used in the numerics, as we will see. And then you have this term that is what people call the hopping, that tells you that your particles, so your fermions in this case, can jump, of course, from one side to a neighboring one in the lattice. Now here you have two energy scales, so let me define the ratio delta over J, and let me call this the strength of the disorder. So of course, the wider you make this distribution, this is given by delta, the more different are the values of your local fields, and therefore the stronger is the disorder or the fluctuations of these fields in your system. Okay, now a comment that is maybe trivial for most of you, but let me just stress that what I'm writing down in here is actually not just one Hamiltonian, but a family of Hamiltonians. So you have one Hamiltonian for every realization of your random potential. And the fact that the disorder is quenched means that when you think about time evolution of this system, you are choosing one realization of the disorder, and then you run your time evolution, keeping the disorder fixed. So you do not allow for fluctuations of these local fields. But then, of course, as usual, when you have randomness, what you want to do is to characterize what is the typical behavior of your system. So what happens, when I say typical, what I mean is what happens with probability 1 with respect to these disorder realizations. So this means that you look at the time evolution of with one particular Hamiltonian, but then you have to do some statistics. So you have to introduce probability distribution, and you have to somehow argue that what you are trying to say holds for most of the realization of the potential that you are considering. Okay, so this is ingredient number 2, and this is, as you see, this is a quadratic Hamiltonian, so this is, of course, a single particle problem. You can add many particles, but they will be non-interacting. So this is what you use to describe Anderson localization. Whereas, of course, if you want to talk about MBL, you have to add interactions. And these interactions are local in space. So what you can do is you take your Anderson Hamiltonian and you define a many-body Hamiltonian by adding some interaction term, which could be, for example, a density-density interaction where you have that two fermions see each other only when they are at neighboring sites of your lattice, and the amplitude of their interaction I encoded into this coupling constant U. Now this is a Hamiltonian for fermions. Let me write down another Hamiltonian that you find very often into this MBL literature, which is some disordered version of your XZ spin chain. So if I keep the same notation here, I would have the sum over all my sites of, again, the local fields, and now instead of the number operator, I put my Pauli matrix, sigma z. Then I have the hopping. The hopping, I can write it in different ways. So I will write it as sigma x plus sigma y. But this you can also write as sigma plus sigma minus plus sigma minus sigma plus. So this describes you spin flip which propagate across your lattice. And then the interaction becomes an Ising-like term with 2 sigma z. Okay? And the reason why I'm putting them together is that you know that when you are in one dimension, so you have a chain, these two Hamiltonians are essentially equivalent, so you can do Jordan-Wigner transformation, and you can map one model into the other. And 1D is really the case we will be focusing on when discussing the interacting case. So I will comment about dimensionality, but somehow the idea is that nowadays people in the community are convinced that through many-body localization you can have it only in one dimension, and in 2 dimensions you can have something which looks like MBL, but which is not actually as strong and as stable as what I'm going to discuss in here. So whenever I have interactions, I will somehow assume that we are restricted to 1D.
Yeah, so I'm wondering what happened if the local interactions are also disordered? Will it also introduce some kind of localization as well? Like, for example, this U is homogeneous along the chain, right?
Yes, no, you can put it, you can have it random.
But does it change the physics, or it's essentially
no,
the same?
actually, it makes sense to have it random because somehow when you write down interactions terms like this, so if you go to first quantization, they will contain, let's say, the wave functions of your single particle problems, and you sandwich your interaction potential between those, and those are themselves random. So in principle, your coupling also has some fluctuations, and you can put it in general inside and give some heterogeneity to those couplings too.
Okay, thanks.
Okay. Okay, now let me already make a comment here, and let me perhaps try to draw this. So I wanted to stress that already at the level of the ingredients, somehow MBL is a bit at the intersection between integrability, glassiness, and Anderson localization. So I will try to draw a diagram in here. So we have three ingredients. So you have interactions, you have randomness, and you have unitarity. And MBL has all of these, and this matters. Whereas if you put only two of these ingredients, you have in general different physics. So interactions plus randomness is what usually you consider when you look at glasses. Also, if you're interested in quantum glasses, and this is related to what I just said a few minutes ago, namely the fact that usually when you look at glasses, you have a different type of dynamics with a bath and with, let's say, stochastic terms a la Langevin. Then if you have unitarity plus interactions, as you know, we have integrability. And randomness plus unitarity, but without interactions, is Anderson localization. And I will try to convince you that having all of the three together gives rise to some phenomenology that is really specific and peculiar. Okay. So now these are the ingredients, and let me go to how do you see out of equilibrium given this setting. So this is point B. So what I meant with out of equilibrium in my previous definition is essentially two things. So the first one is that you have local memory. And the second one, which is a bit of a consequence of this statement here, is that you have failure of thermalization. Okay, so let's start from local memory. Which is a bit what we saw in this simple one particle case in the figure that I plotted at the beginning. So how do you probe local memory in your dynamics? Well, you do something very similar to what was done in these cold atom experiments. So this is what in Calabrese-Cardi language you could call a quantum quench. So you do some perturbation to your system, and then you see by measuring correlation functions of local operators what happens, how much does your state change under your time evolution. So this is some sort of quantum quench. And the idea in here is that your initial condition, psi 0, has some well-defined local ordered structure, by which I mean basically that you kind of know where are the particles at time equal to 0. And in general, this means that you choose your psi 0 to be an eigenstate of your position operators in your Hamiltonian, so an eigenstate of the Hamiltonian when the hopping is equal to 0. And then your quench will be essentially in this coupling in here, so you switch on this kinetic energy. This is what you do when you release the trap, so you allow this particle to move on your lattice. And you will have a state at a later time, so let's say at time much larger than 1, and you ask whether this is in some sense similar to your initial condition, and when this happens, you talk about localization. So in the case of one particle, it is very easy to prepare such an initial state. You put your particle in one side of your lattice, and that's it. What can you do in the many-body case? Well, let me consider, for example, a one-dimensional chain with sides from 1 to L. And let me prepare an initial condition that we saw already in some previous lectures, where I essentially put my fermions only on the even side of my lattice, and I let my odd sides empty. So this is an odd side. So this is like an L state in density. It is a so-called charge density wave. So this is the density at time 0. And it is the initial state of those experiments that was recalled yesterday in the group of looking, for example, when looking at quantum scars. And this is a state which has some local order. So if I focus on, if I look locally at these sites, I see that there is a structure, right? So I see that I have a particle here, no particle here, a particle there, and so on and so forth. And so the question is, does this structure survive in the large time limit or not? And the way you can measure this, so for this particular initial state, is, for example, by looking at what people call the imbalance, I of t. So this is not really it's a linear combination of correlation functions. And this is defined as follows. So I assume that my chain is finite. I put a 1 over L to normalize things, and then I have a sum over all the sides of my chain of a phase minus 1 to the I, and then I take the expectation value of the local density on my time evolving state. So what this is measuring is, it's called imbalance because it is essentially the difference in density between, let's say, the density that you have on the even side and the density that you have on the odd side. So this is precisely a quantity which measures the type of order that you have in the initial condition, which means that for this particular initial condition, the imbalance at time t equal to 0
shouldn't be L plus 1. L plus 1 side.
You mean here?
Yeah.
Yes. Or let me put 1. Okay. Eventually, I will think about L being large, so that doesn't really matter, but a good point. Okay, so at time 0, this is equal to 1, and then, of course, the question is what happens at much later time. And of course, if you have memory, what you expect is that this imbalance will take values which are still maybe not exactly 1, but quite close to 1. And now I should, I should show you a plot, but I will perhaps draw it because we save a little bit of time. And you have it in the slides. So the idea was to show you a plot, again, from an experiment, which this time was done in Germany in the group of Immanuel Bloch. In Munich, where they did precisely this. So they had a system of cold atoms. They prepare it in such an initial condition, and they measure precisely this imbalance quantity in here. And what they find, so they have the Hamiltonian, you can think of this in the Bloch experiment, is more or less this. When I say more or less, is because actually the potential that they have is, so you have to come up with a way to realize random potential, and they use a quasi-periodic potential, so that is not really a random potential, but for the purpose of what I'm saying is as if you had a purely random potential. So quasi-periodic means that you, to create these local fields, you superimpose two lattices which have a length scale which is incommensurate, and so what comes out is something very irregular that you can think of as a random potential. But apart from that, you have interactions and you have your kinetic term. And the result is this, so forgive me for drawing it and not showing the data, but you will see the plots in the slide. So the idea is that you have time measured in some units, so the inverse hopping typically, and you have your imbalance, which starts from 1. And you have different curves depending on the strength of the disorder that I remind you was this ratio in here. And here we are keeping U fixed. And we tune delta over J. Now the different curves will look a bit like this. So the bottom curve here corresponds to delta over J equal to 0. So it's the case where you do not have disorder. And then moving up in here, you are increasing the strength of your disorder. And now what you see is more or less what you expect. So first of all, if you have no disorder, you have your imbalance, which very rapidly decays to 0 and remains equal to 0. And this is telling you that during your time evolution, you really washed out all the information about the structure of your initial conditions. So this means that your particles will move, will scatter with each other, and eventually you reach a density that is uniform, so the imbalance will be equal to 0 at large times. But as you see, if you make the disorder stronger, this is no longer true. So the imbalance reaches some sort of stationary value, but this stationary value is different from 0, and it gets closer and closer to 1 as you make the disorder stronger and stronger. So the fact that you have a plateau here at values different from 0 tells you that you have memory which is, I stress it again, which is local. So you probe it with local densities and you see that the structure remains encoded in your system. Okay?
Can I ask a question?
Of course.
When about this plot, when t goes to infinity, these curves in the middle will go to some constant, or they will decay to 0?
I didn't hear, but perhaps you're asking.
Let me repeat the question.
So you're okay. So this is a good point.
Yeah.
So in experiment, you will have a cutoff, of course, because you lose atoms. So this is cut off at a time scale which is related to how much you manage to keep your system isolated and to keep atoms in your system. But this is a good point, and I will come back to this. So strictly speaking, if you really think theoretically at many-body localization, in the sense that you have a system that really never couples to the bath, and your dynamics is unitary forever, then you would expect this plateau to go on forever. And this is what I meant when I wrote permanently out of equilibrium in my definition. And this is different from what you have in glasses, for example. But I will come back to that in a second.
Okay, thanks.
But I'm not sure this was the question, actually, because I didn't...
Yeah, that's indeed my question.
Great. Okay, so this was about memory. And now let me just say what does it imply for thermalization. So now I will sketch something, and then I will be more precise in discussing question 2, but let me just give an idea of what are the consequences of this if you think the system in terms of statistical physics.
Question. How much was this L parameter in the experimental setup?
Ooh.
More or less, more or less.
No, in the experiment, I think it was around 50 or so. In numerics, you do 24, I think is the threshold. So all the numerics that I will show is done for system sizes that are small. But yeah, in the
And there's also a related question in the chat, maybe.
Yes. Yes, exactly. So we will comment about sizes and so on. I think that the cutoff is, of course, also related to the size of your system. So when you think about experiments, you have to keep it in mind. Now, for the moment, of course, here I'm jumping back and forth between finite size and infinite size. But when I speak about thermalization, I will always assume that you are taking a thermodynamic limit at a certain point. So the true thermalization or absence of thermalization, you define it assuming that you have this limit of infinite sizes. But of course, in experiment, what you see is out of equilibrium within the timescales you have access to, which are related also to the size of the system which you have access to.
There is another question.
The question is, as disorder strength increases, the imbalance approach is 1, meaning that I have a system where memory is totally preserved. Well, that is the limit where it would be really the j equal to 0. Oh, I forgot j here. So for the imbalance to be strictly equal to 1, you really have to kill this kinetic energy. And that's a little bit like in the single particle case. So if you allow a little bit of kinetic energy, then you will spread a little bit. And if you instead completely kill this term, then of course you have a system which, I think in terms of particles, for which the initial condition that I draw is really an eigenstate. And so in that case, your imbalance does not evolve and it remains equal to 1. I hope this answers. Okay, so let me tell you what this implies at the level of thermalization. So what would thermalization imply here? Is the following. So you are looking at the expectation value of these local densities. Okay. And what you would expect if your system thermalizes is that if you take some long time limit, and here I take 2 limits, as I already said. So you have in mind that you are taking this long time limit, but also the limit of infinite size. And I will really go back and comment on this in question 2. This is related to the fact that you want to kill quantum revivals in your system. So if you take these 2 limits together, then what you would expect is that your expectation value really reaches a plateau, so it reaches a value that does not depend explicitly on time. And if you thermalize, what you want is that you are able to compute to get this long time limit by computing a thermal average, so by computing the expectation value of the same local density with respect to some Gibbs-like density matrix. So the expectation value beta of any operator A, I define it to be the trace of the operator with respect to some density which depends only on this inverse temperature beta, and that is e to the minus beta h. So in here, I'm assuming that I am conserving only the energy, so I put only the energy at the exponent here. and beta is the usual inverse temperature. And how do you fix beta on the right-hand side? Well, you use precisely the fact that you are conserving this energy. So you use that you have a well-defined value of energy at time 0. So this is the trace of your Hamiltonian against the density matrix at time 0 that I call rho 0. And what you do is you impose that this expectation value is equal to the expectation value of the Hamiltonian itself with respect to this Boltzmann-like matrix. So this is an equation in which you have the left-hand side fixed by your initial state. You don't have beta, so it is an implicit equation for your parameter beta. Okay? Okay, now let's see why, in the case of the imbalance, this is not happening. So let's work out this example again of our quench. And let's start by computing what would be the temperature corresponding to the initial condition that we have. So now I will rewrite my initial state in the so-called computational basis. So this is an eigenstate of my position operator. So I had a density at position 1, which was 0, a density at position 2, which was 1, a density at position 3, which was 0, and so on and so forth. Okay. And then I compute, okay, I introduce now the energy density. So this is just the energy divided by L. And I compute this diagonal matrix element term of the Hamiltonian. And what I see, so I should have, okay, let's look at this. Now I have fermions, not spins, but the point is the same. So if I choose this particular initial state, what I see is that I will kill these two terms. The density at two neighboring sites is equal to 1 for one site and 0 for the next one. So this term vanishes. And the same happens for the kinetic term here. So what remains of this expectation value is essentially the potential. And what you save is only the potential on your even sites, even where your density is equal to 1. And this contributes with your random local potential, and then you divide by L. Okay. So here you have some sum of random variables which are independent. So let's think about L large. What we know is that when L is large, we can apply central limit theorem to estimate the size of the numerator in here. So the numerator will scale like the typical value, which is delta, times the square root of the number of terms that we are summing on, which is square root of L, and then we divide by L. And so you see that when L goes to infinity, this goes to 0. This is what people call being in the middle of the band. Okay, let me go there. And what they mean is essentially that you are in the middle of the spectrum where you have exponentially many eigenstates. So if you draw energy here versus, I will draw an entropy. So the log of the number of my density of state, of the log of the number of eigenstates, for example, at a given value of energy, and then maybe, okay, I can normalize it or not. But okay. So in this type of tight binding modus, I typically have a spectrum which is bounded. So down here I have the ground state. Here I have the most excited state. And then I have an entropy that looks more or less like this, typically. where most of my states are concentrated in here, where my density of states becomes flat, which is the middle of the band. And your particular initial condition is precisely in this region. So I'm drawing this because I want to somehow stress the fact that when you discuss about MBL, you really think about states which are highly excited. We are very far away from the other limit that was considered, for example, in the lecture by Sachdev, where he was basically down here looking at excitations on top of the ground state, and he was showing this plot and pointing out that typically here you have much less energy levels and a much bigger gap, whereas if you go in the middle here, you have a gap between levels which is exponentially small in your system sizes. Yes, it's. Which two limits? Ah, yes. Again, I will okay, wait for let's say, question 2. But I can already say that, so this is a very strong limit. This is a very strong thing I'm asking. So I'm asking that really I kill all time fluctuations of my expectation value. And if you have a system which is finite in size, this never happens because you know that you have a so-called quantum revivals. So you have some sort of times which can be very large, where nevertheless this time dependence shows up, and you actually get, at those times, your expectation value gets as close as you want to the one that you had in your initial condition. So this is what is meant by revivals. Typically in these many-body problems, the times, so this depends on the system that you are considering, but typically the time at which you have these revivals, you may expect that this scales like the gap between the energy levels, so this will be, in general, exponentially large in your system size. So one way to realize this revival effect is to take your thermodynamic limit so that you reach a long time limit, which really is time independent. Now you can introduce weaker notions of equilibration and thermalization, which are so-called equilibration and thermalization on average, where instead of taking strictly the infinite size limit, you introduce time averaging of quantity, and this will your fluctuations and your revivals. And as I said, I will comment a bit more on this when discussing question 2. But yes, so in principle, the order matters in the sense that to have really this strong definition, you want to take n going to infinity before and then t going to infinity afterwards, or t which goes to infinity with as fast as this principle.
Okay, thank you.
Yes, maybe it's now I just finish 1 minute. I just want to say, so we are here at zero energy, oops. And what we can do is now we can work out what is the temperature which corresponds to zero energy density. So you can do the calculation with your expectation value, but you can also use thermodynamics here. So you remember that the inverse temperature when thermodynamics works is related to the derivative of the entropy with respect to the energy. And in the middle of the band, you usually have a flat density of state. So your derivative is equal to 0. So you are at beta equal to 0, which means that you are formally at infinite temperature. And now I just write one more line. So then you can ask, you have your temperature, so what would be the thermal value, your imbalance, so the value that you should reach if your system thermalized? Well, this is 2 over L, sum I from 1 to L minus 1 to the I, and then you have the thermal expectation value of your local density. Now, what is the thermal expectation value if beta is equal to 0? Any guess? Okay, I only see that there are audio problems. Okay, you want to stop and we check the audio and then... Okay, so let me just conclude here. So if you compute this at beta equal to 0, you will find... So this is what? This is now the trace with respect to a density, which is the identity. So the normalization gives you... I can compute the trace in whatever basis I want. So I choose the basis, the computational basis, the basis of eigenstates of my local densities. My normalization gives me the dimension of Hilbert space, so the number of states that participate to my basis. And then when I compute the expectation value of this density, I will have half of the states which contribute with a factor of 1, and half of the states that give me 0. So here, I will get a factor of number of states in the basis divided by 2, so this is 1/2. So indeed, thermalization would imply that you reach a density profile locally where you have half probability to find a particle there and half probability not to find a particle there. And if I plug this in here, so this is 1/2, I bring it out of the sum, and then I have a sum of alternating values, and so I see that this is equal to 0. Let's assume even number of sites. Okay, so this is what happens without disorder, as we saw, but the fact that the imbalance reaches a stationary value that is different from 0 is telling me that all of this picture breaks down, and that this convergence does not hold true in this system. And actually what I find, and now I really stop, is that instead my local expectation values, they do converge to something which looks stationary, but this something is not the thermal expectation value. It is actually quite close to the value that you had at time t equal to 0, which was not 1/2, but either 0 or 1, depending on whether I'm looking at an even or at an odd site. And this is something that I would keep in mind, because this tells me, in some sense, that my local densities are almost conserved. By the dynamics. And I will come back to this observation when discussing relations to integrability for MBL systems, which is question 4, I think. Okay. Oops.
Okay, so let us ask if there are any questions.
I have a question, and that's, you said that the state is in the middle of the band, and my reasoning is that just a diagram how you draw it means that the energy 0 is in the middle, but is that the reason, or why do you say that a state with energy density 0 is in the middle of the band?
I couldn't hear you properly.
Could you write it down, because we are sorry we don't hear very much your voice. In the meantime, maybe there are other questions.
Perhaps you're asking whether my drawing of the density of state is generic. Okay, so the question is why having 0 energy density means necessarily that you are in the middle of the spectrum. Well, okay, this may depend, of course, on the feature of the particular system that you are looking at. So for most of the Hamiltonians, now okay, you can come up with models where this is not true, I guess, but I would say that it's rather general that, so you can think it in this way. So let's extract a state at random from your system, or even an eigenstate at random, and this will, so when you do this, you pick up, so these eigenstates will typically have an expectation for the structure of the local Hamiltonian that you write down. We'll have an expectation which is 0, and this you are in the region where your entropy is maximal because you are extracting it at random. So you pick ones which are most numerous, and you usually find that this maximum is attained far away from. I mean, if you have a symmetric spectrum, it will be attained in the middle. But no, I agree. I mean, this is something which happens in general, but you may come up with models where your density of state has peculiar features, and the entropy takes a maximum which is not exactly at 0. But I would say in general for these random systems, this is what you'll see if you plotted the density of states.
I have a question. I don't know if there is some other ones. But why you are assuming this? I mean, you could have said that the expectation value at t equal infinity could have been calculated from the diagonal ensemble, and then compare with this result instead of with the Gibbs one, no?
Yes. So if I, in here, to make it, to distinguish between what I would like to call relaxation, so the fact that you indeed kill fluctuations and you converge to diagonal ensembles, that is assured by the fact that you have dephasing, and you do have it in MBL, with thermalization, where I really mean that you take your conserved quantities and you write down an expression of this form. So in here, you do have relaxation. So you have this first part. You do not have this first part. And you understand what this looks like precisely by looking at the diagonal ensemble and at the structure of the eigenstate. And you will see that there is no ETH in there. And therefore, this equality is not there. But you do converge to the diagonal ensemble. So maybe, was it an answer? So you're telling me you're asking too much, you're putting too much restriction to. Yes. So this is why I wanted to. Okay, it's maybe a personal definition. So this part, which I would interpret as convergence to the diagonal ensemble, I want to call it relaxation and thermalization. And this, I want to call it thermalization. But we can on terminology. And the fact that there was a question that the density of states peaks at 0, I don't think it's a feature of disordered systems. I think it happens for many local Hamiltonians of this type.
There is a question about this last one.
Very good. Thank you, Saranio. Let me read it to the audience. Or if you want to speak up.
I don't think I'll be audible. Given
No, you're right.
audience.
So Saranio is saying if there is a particle symmetry and you have a bounded symmetric spectrum, then the maximum you have it at 0.
Yeah, but shouldn't we consider macro-chronicle ensemble instead of just micro? Because the number of particles also conserved.
Yes, so here I'm putting myself in a very good. So I'm putting myself in a sector with fixed n. And when I write this, I am assuming that thermalization holds, and then I have equivalence of ensembles. And so I can switch from canonical to microcanonical. And very good point, I'm in a sector of fixed number of particles. Okay.
Okay. Well, I have a very last comment. Actually, you have an Hamiltonian where the interacting part is nearest neighbor. And you start from an initial state which is built in such a way to kill exactly that term. So it is a kind of a very peculiar setup, not so universal at first sight.
Yes,
Can you
absolutely.
comment on this?
Yes, so indeed, when looking at this imbalance experiment, you may ask, are you really probing MBL, or you're just probing Anderson localization, where the interaction doesn't matter? And this is a good point that Bloch also has in mind and discusses in some later papers. But we will see that, so from the point of view of the imbalance, this really looks like what you would get in an interacting system. But there are other quantities where you really see the difference and the role played by interactions. And we'll come to that. And one of these quantities is entanglement growth during time evolution. But it's true. So far, you could put u equal to 0, and you would get the same picture, more or less.
Very last question on the chat. Two actually.
I beta gives 0 only at infinite temperature. No, in the sense that, I mean, what you need to get 0 is to forget the dependence on the site that you're looking at, so that you bring it out of the sum and you get this sum of alternated sum. So if you have a temperature, if you thermalize to something that gives you an arbitrary value for these local operators that does not depend on position, and this could happen here, then you would still see this. The point is that when you ask for thermalization, somehow what you expect is that whatever density you probe locally in your system, you get the same outcome. So you have no dependence on the particular site that you're looking at. So locally, your state looks similar, independently of where you're looking at, and it looks like a thermal state. And this is what would give you this mechanism of getting 0.
So this will be now there is another question, it will be the last, and then we will make a break. So please. There is answer.
If we started from some initial state, yes, with less than minimal imbalance, would we get similar plots? Yes, you could also maybe, and I think they did it in experiments, start with, they did it in 2D, start with a density like this, and you try to see if you even out in the middle. So I think the reason why they really chose this superordered structure is that play of thermalization and disorder. So maybe I will postpone these. I will copy paste them, and I will postpone these to the question 2 discussion, if everybody's fine in the chat. Okay. Okay, so regarding this imbalance thing, I just wanted to make a few remarks, and some came up already as comments from the chat. So the first remark is as follows. Is this working? Yes. Okay, so we are talking about ergodicity breaking in here, and I wanted to stress that this is, okay, it is ergodicity breaking in the sense that your dynamics does not allow you to somehow explore all of the space in Hilbert space that you would expect to be accessible just by energy conservation. But it is an ergodicity breaking that, let's say, does not, or it is not related to symmetry breaking showing up in your partition function. Okay? And what I mean by this is that the scenario that you have in here is different from what you would expect. For example, think about Ising systems. Where you can also, you have symmetry breaking, and then you talk about ergodicity breaking, and you see this in your partition function at low temperature, because you have a partition function which clusters into states, and these two states, you can distinguish them in terms of symmetry and magnetization. And something similar happens also for certain disordered systems, such as glasses, when you speak about the so-called static. Sorry, I'm writing very badly. Static transition temperature in glasses. So just to give an idea of what I mean in here, so let me remind you what is the scenario that you get in glasses. So now I will think about classical systems, but to some extent one can generalize this to quantum systems too. And I think about a dynamics which, as I said, is different. So in usual mean field glasses, you have stochastic dynamics a la Langevin, so you have a temperature. You can compute your partition function, and you find in mean field models. So in particular, let's think about the p-spin model that was mentioned already in some of the lectures of last week. What you find is that you have two transition temperatures, which are different from each other. So I call the lowest one, I call it the static transition temperature, and the higher one, I call it the dynamical transition temperature. This is T equal to 0. And what you do when you characterize the static transition temperature is you compute your partition function. This is a random system. You have to introduce tools to compute this function, which usually go under the name of replica method and replica calculation. And you find that your partition function changes, if you want, when you cross this temperature. So in the low temperature phase, you have a structure in your Boltzmann measure where you see that your measure collapses into a certain number of states, which is not 2 as in the Ising case. It is typically larger than 2, and these states have all a complicated hierarchical structure that you have to describe with the so-called replica methods, and this is related to replica symmetry breaking. But this is a thermodynamic thing, so it is something that you spot when you look at really the partition function of your system. On the other hand, there is this other transition temperature that people call the dynamical transition. And this is related, so if you cross this temperature and you look at your partition function, you do not see anything special happening in there. But you do see something happening in the dynamics. And you see this if you do quenches that now are not like the quantum quenches that we were thinking about, but are more the usual classical quenches where you change the temperature of your system. So the idea is you start from your system, which is at equilibrium at a given temperature that is high. So you extract a configuration from the Boltzmann measure, let's say at this temperature here. And then you quench to some temperature that is, let's say, lower than this critical one. And quenching means that you then run your Langevin dynamics with this new temperature in here. And you ask whether your system thermalizes to this new temperature. So you can compute the expectation value of the energy and ask whether in the long time limit you converge to the expectation value that is predicted by thermodynamics at this new temperature you're quenching to. And now what you find in this type of models is that if you quench above the dynamical temperature, everything works. So your dynamics thermalizes very fast, exponentially fast. But if you cross this dynamical temperature, you go out of equilibrium. So the dynamics of your system starts slowing down. It displays these out of equilibrium features that people have characterized at length, which are aging and so on. But the point is that you do not converge to, for example, the expectation value. So if you look at one-point function, they do not converge to the thermal expectation value at the temperature that you are using to run your dynamics. And this, as I said, is a phenomenon that is purely dynamical in here, whereas if you compute your partition function, you do not see anything. It is smooth if you cross this dynamical temperature. But the dynamics is telling you that if you go below this temperature, in some sense, there is no point in computing this partition function because you simply do not converge to a long time limit that you can describe and capture using this thermodynamics. And this is precisely what, or the way you can think about this, this MBL. So the type of ergodicity breaking is more similar to this dynamical, let's say, glass transition. Or also to quantum integrability. Where you also know that you do not converge to Gibbs-Boltzmann-like partition function. But there are two crucial differences, and this is what was stressed in the definition. So the first crucial difference is that you expect, at least in the longest definition of many-body localization, you expect that this type of ergodicity breaking is permanent. Which means that morally, if you are able to keep your system isolated forever, you would see that your plateau would go on forever in your time evolution. And so we are not talking about metastable states in here. Which would correspond to the fact that eventually, if you have a metastable state, maybe this metastable state is very long-lived. So these are like prethermal states, if you think about breaking integrability. So they may be very long-lived. You may have timescales which are parametrically large in some parameters of your Hamiltonian, but in that case, at a certain point, you know that you will eventually relax to some equilibrium state. Now here, this is not the case. So of course, it is not realistic to think that your system is isolated from the environment forever, but let's say conceptually, you would have your MBL state, which is not metastable, and this is different with respect to glasses in finite dimension. And what I mean by this is that, okay, this picture that I'm drawing in here is a picture that holds for models of glasses which are mean field, so where everybody talks to everybody else, like Sherrington-Kirkpatrick, or this P-spin model that is kind of related to or the matrix model like that was discussed last week. And these mean field models really display this dynamical transition. And the fact that you have a dynamical transition emerges because you have many metastable states in your system, so many minima of your free energy, that are separated by barriers in free energy, which are actually scaling with extensively with, if you are in mean field, they are scaling extensively with the number of your degrees of freedom, so they are in a way scaling extensively with the dimension. So here you're taking dimension to infinity by looking at the mean field limit, so you have this infinite barrier. And what happens is that if you are in such a mean field situation, in some sense, you look at your partition function and you do not see all of these different states separated by barriers. You are averaging over all of those, and and this average gives rise to to something which is a paramagnet, which is replica symmetric in here. But if you do the dynamics, what happens is that you are initializing into one of these states, and your dynamics keeps you trapped into one of these states because the barriers are too high and you cannot escape. And this is what you are probing and what you see when you look at this dynamical temperature. But there, this is a feature of mean field. So the barriers are extensive, they scale with the dimension. So if you go to finite dimension, this transition in here, which is well defined in mean field, is rounded, and you actually get a crossover and not a true transition. Whereas in here, we are talking about a system where you expect to have a sharp dynamical transition in finite dimension, so in particular in dimension equal to 1. So this is, I would say, a difference that one has to keep in mind with respect to glasses. And the second difference is instead related to quantum integrability, and it has to do with robustness. And robust in here is with respect to changes of, if you want, the parameters of your Hamiltonian. So of course, it's robust with respect to fluctuations of potential. So you have a random potential and you want this phenomenology to emerge for almost all your realization of the potentials. This means that it does not rely on choosing precisely your local fields, but you can also change a little bit your couplings to some extent in your Hamiltonian, and you will still have this phenomenology of MBL. Of course, it is robust, I stress it again, as long as you remain into this framework of unitary evolution. As you add some temperature, this is washed out, and you cannot talk about localization in the way that I described it so far. And this is different with respect to integrability, because you know that to have quantum integrability, you have to somehow tune these parameters to be at an integrable point, and there you have all these Young-Baxter, Bethe-Ansatz, all of these nice features of integrable systems. So this is a bit why I think the community is happy about these systems and finds them potentially interesting. And just to comment a little bit more on this, so of course you can change a bit your parameters, but not too much. So all of this phenomenology relies on the fact that you have sufficiently strong disorder, as we will see. So if you make the disorder too weak, you will typically have a transition. So this is delta over J, and let me keep U fixed, for example. So if your disorder is, if your disorder is strong enough, you have this out of equilibrium MBL phase, but if you make it too weak, then you will eventually transition to some delocalized and thermal phase, where eventually your imbalance, for example, will decay to 0. You can compute partition functions to characterize the long time limit, where transport, as we will see, is restored, and all this. And you expect that there is some transition at a critical value, and this is precisely a dynamical transition. And the MBL is a dynamical phase. So it's not a point in your configuration space, it is really a phase, a region where, which is stable with respect to weak perturbation in the strength of your disorder, for example. Okay. So this was about part B. And now I wanted to come more into the issue of transport, because as you saw in my tentative definition, I stressed that there is a reason here why you are out of equilibrium, and this is that transport is suppressed. And I will spend some time on this. And I'd like to start by recalling what happens in, let's say, generic systems. By which I simply mean systems which are not MBL. And what happens in here is that you have conserved quantities. Which are, for example, the total energy, which are, somebody spotted other conserved quantities, which are the total number, for example, of fermions in your system, which can be the total spin in the z direction, or if you have charged particles, this could be the total charge, which is related, of course, to conservation of the number of particles. And during your dynamics, for example, if you do a quench, what you expect is that you start, so you conserve the total energy, but you can create initial states where you have some local imbalances. And what you expect is that, indeed, during time evolution, these imbalances even out, and this means that your energy is transported from one region of the system to another one. And the way it is typically transported is either ballistically, which happens for free systems or systems where you conserve some momenta, also for CFTs, for some integrable systems too. You have ballistic contributions, or more generally diffusively. And if you want to play with this, there is one exercise which is just about transport for free particles that you find in the notes. Okay, now this scenario breaks down when you are MBL. So when you are MBL, what you expect is that, so I will write it down and then I will explain. So the dissipative transport coefficients. And when I say transport coefficient, what I mean is the diffusion constant or the conductivity, if you think about charged particles. These exactly vanish. Because of the disorder. So what I'd like to do now is to explain a little bit more precisely what you mean by this. And this is, if you want, connected to the original notion of localization as it was thought of by Anderson back in '58. Okay. So I would just like to recap a little bit how you compute these transport coefficients and what exactly you want to be equal to 0 when you are MBL. So this will be a bit of a recap of linear response, basically. Okay, so the way you think and define transport coefficient is usually through linear response. So this means that you have your Hamiltonian, which does not depend on time, and what you do is you add some perturbation, which we assume to be weak, which may depend on time. So you have a field, and you have an operator which is coupled to your field. So the simplest case that you can think of is an Hamiltonian of spins, where this is the magnetic field, and the operator to which you couple is the magnetization. It's a question? No. Okay. Then you assume that without this driving, so without this perturbation let's say that the expectation value of your conjugate operator was 0. So what you are interested in is to compute what is this expectation value, or if you want, the variation of this expectation value if you add the field. And linear response means you want to only the linear order term of this variation with respect to the field. And in general, you may assume that this will be an integral over all your times of some kernel that I will call a susceptibility times the field at the time t prime, and then I have higher order terms, which I don't care about in the following. Okay. Now what I can do is, let me assume that I have, I want to go to frequencies, so let me assume that I have time translation invariance, so this susceptibility depends only on the time difference, so that I can write this convolution easily in frequency space. So let me take one value of frequency, and I would just get a product between the susceptibility as a function of frequency, the component of the field at that frequency, and then I have higher order terms. Now, in general, if I go to Fourier space, this susceptibility can have both a real and an imaginary part. And people usually denote this as follows. So the real part, they put a prime, and the imaginary part, they put a double prime. And this is what they call the reactive part. And this is what they call the dissipative part. So we are interested mostly into this imaginary part. Now let me stress that if you take a frequency which is, you are in the complex plane, so you have some property of these functions being analytic. So using this, if you are, for example, in the upper half of the complex plane, you can create imaginary part with real part, so the two are not independent. But for the moment, let me focus on this dissipative part. And let me tell you why you call it dissipative. So here, I'm not going to do this exercise, but what you can show is, for example, if you choose your field to be precisely, to have one single frequency, so let me call it f cosine of omega t. What you can show is that, so you drive your system with such a field. Of course, now you have a time dependence, so this means that energy is no longer conserved in your system. And you can compute what is the change of energy in your system. And since you have a periodic thing, let me average this over one period. So 1 over the frequency. And what you can show, so this is an exercise, is that you will find these changes in energies are related precisely to this imaginary part. So you will find a proportionality relationship with this key second evaluated at the frequency which is resonant with the driving. So indeed, term dissipation has a meaning, so it has to do with the fact that you are injecting energy into the system by driving it, or that you are dissipating it out of the system by means of the driving. Okay, so to understand this quantity better, let me make another comment. So, and the comment is that when you think about dissipation, this is usually related to processes which are not time reversal invariant. So when you have dissipation in your system, you are breaking, in general, this symmetry of time reversal. And one very simple way, or sketchy way to see this is just to remember that this imaginary part, well, you can write it as key minus complex conjugate of key. Then you use the fact that you have a representation of this. This is a Fourier transform, so this will be equal to 1 over 2i. Then you have the integral over time of e to the I omega t. And what I do is, so I have the first term, which is key. I want to subtract the complex conjugate, so I would have a minus in front, and I absorb the minus in the time, and I flip the sign of the time, so I can write this as the difference of key of t minus key of minus t. And this is just to stress that whatever contributes to this dissipative part, you see are processes which are not in general time reversal. And you see this explicitly. This is odd with respect to time reversal. So the type of transport that we are interested in when looking at this dissipative term is related to time reversal. Okay? Okay, now how do you compute this susceptibility in general? Well, what people use is to go back to let's say fluctuation dissipation, if you Kubo formulas. So you look at these works by Kubo, which is, I think, just 1 year before Anderson, in 57. And what he derives within this linear response framework are relationships that are, let's say, between correlation and responses. So you relate the response of your system, which is what you want to characterize with this susceptibility, to correlations of the conjugate operators O. So the idea is that this chi of omega in general, you can write it, sorry, let's look at the time domain. And then here you put the commutator of your conjugate operator at different times. So this is a correlation function. And you average this with respect to a density matrix that I call equilibrium, where the idea is that this density matrix is equilibrium with respect to the perturbed Hamiltonian. So you want that this object here commutes with the Hamiltonian when you switch off the field. And usually people think of this as being of the form e to the minus beta h. But I think the requirement is weaker, so you just assume that, that you have that stationarity, that you commute with the Hamiltonian. So this could be, for example, what you get when you try to solve your Boltzmann equation and you reach your long time limit, describing the state of your system at large times. Okay, so we want to use this, and we want to use this for the conductivity, because this connects more with what perhaps Anderson was thinking about. So really understanding localization problems as the fact that you have an insulator. So if you have electrons, you do not have current propagating of these electrons. And for the conductivity, we need an extra step. So the conductivity sigma is what relates linearly a current operator to the electric field. And this current operator, well, if you think about fermions in a lattice, you can define it as your hopping coupling J, and you sum over your sides, C daga A, CB minus C daga B, CA, and I put an I in front. Just for complex conjugation of this object here. Okay, so now I will write down the Kubo formula for the conductivity. And I will write it as follows. So I take directly the imaginary part, or the dissipative part, and I choose a frequency omega which is real. But I will have to, when I do this, to put a regulator to do the Fourier transform. So let me introduce this theta in here. Let me normalize by the volume of the system. And then I will have the real part of a phase here. So you see that eta in here regularizes my exponential so that I have convergence. Then I have the commutator of my current on this equilibrium density. And then I have an extra factor of omega in the denominator. So one may be a little bit confused. So you see I have a real part instead of an imaginary part, and then I have omega here. So this doesn't quite look like the Kubo formula that I wrote on top. And this is due to the fact that when you think about electric fields, the way you couple in your Hamiltonian to the current is not through the electric field itself, but it's through the vector potential. So a field A, which is related to the electric field by a time derivative. So when you go to Fourier, so the true proportionality relationship you would have between the current and the vector potential. And now if you want to write a proportionality relationship with the electric field, you have this extra derivative that in Fourier space gives you a factor of I omega. And this is what you see here. So you have an omega, and then the I am absorbing it in the fact that instead of taking the imaginary part, I take the real part. Okay? But this you can work it out if you're interested. And now what you do, so the precise claim is that this will have a frequency dependence, and in particular, it will have a so-called DC component which corresponds to zero frequency, and then you have at small frequencies something which can be even non-analytic with some exponent. So it will, in general, look like this. So it decays at large frequencies, you have a maximum somewhere, and you have a non-zero point where you intersect at zero frequency. And the claim is that in MBL, it is this DC component that is equal to zero. This is a good question. So the question is about how do you define many-body localization eventually? And I think there is not a unique way to think about this. So I think originally you think at MBL in these terms, so you really want to, so I had in the slides, I really have the abstract of Anderson's paper where he characterizes what's going on as the fact that in these random lattices you have no diffusion. So this is, if you want, a strict definition of MBL, and I like it because it is really peculiar of this disordered system. So in glasses you have diffusion. In integrable system you have even Drude conductivity, diffusion constant with delta of omega, so you really have transport. And here you have no transport, so I think this is really a good way to think about these problems. Now, two comments. The first one is that, as I will say in a minute, this is very hard to check. So when you do numerics, you don't want to check this. What you want to check are rather notions which are related to whether you thermalize or not, and you have ETH or not, because those are one-point functions which are easier to compute. And so those are the type of definitions that are mostly used in the numerics. And the correspondence, I think it's not one-to-one. So what people see is that there are regions, at least in the numerics, so there are regions in this disorder diagram where from the point of view of ETH, it looks like your system thermalizes, but still transport is still subdiffusive because you have the disorder. So if you really stick to this definition, you would still say that it is MBL, but then ETH works. So there you have to somehow choose which definition to use. And there is another comment that I can make in here, that is that whenever you talk about transport, you need conserved quantities to be transported. And if you're interested in defining MBL, for example, for periodically driven systems, as people do, this rules out this type of definition. So you have to go back to non-thermal phases and violation of ETH. So it's subtle, but still I like to present this because, first of all, it's the original way you think about this, and also it is very peculiar of this disorder system. So the physics is really also related to transport, in my view, so it's good to point this out. Now, let me try to give an idea why this is complicated to compute. So what would you do? Well, you would try to write down an expression for this using the Kubo formula. And if you think about numerics, you would start from a finite size systems where you have eigenstates and eigenvalues of your Hamiltonian. So you assume that you do exact diagonalization, you get this eigenstates and eigenvalue, and you compute Kubo formula, writing down in lemon representation. So you plug this decomposition of the identity in terms of these eigenstates. And if I do this, so I go back to the formula up there, and maybe I will write you directly what I find. So this is, I still have these limits. Then I have a double sum over these eigenstates. So to compute the commutator, I sandwich my current on two eigenstates, which are labeled by alpha and beta. So I will have the matrix element modulus square of my current. So this is a short notation for E alpha, J, E beta. Then I have the contribution of my rho equilibrium, expectation value on the eigenstates. And let me put the omega in here. And then I have the time integral. So you see I'm assuming a finite system, so I can commute the sum with the integration. That doesn't have issues so far. So what I'm left with is the real part of this integral over time of e to the I omega plus I eta t, and then I have the phase which comes from the time evolution of the current operator. So I combine everything. E alpha minus E beta plus I eta t. Okay. And now I do this integral, or actually I compute the real part of this integral. So I can integrate this phase. I get 1 over I times this object in here, and I take the real part. And if I take the real part, from here what I get is a function that I call f alpha beta eta omega. And that I will write down explicitly. maybe I will just write it down and then we can stop. So this F alpha beta eta omega is a Lorentzian when eta is finite. So it is eta, okay, I put a pi here, and I divide by pi. So it's eta over pi, omega plus E alpha minus E beta square plus eta square. So this is a Lorentzian where I have a preferred frequency that is this energy difference. And this function peaks at this frequency, and the height is of order 1 over eta. And the width in here is of order eta. Okay? And now I stop with one comment, and then we go on next time, because it is related to this issue of order of limits, which comes up continuously in here. And the comment is that indeed there are many limits, and the order matters. So in particular, if I try to compute the zero frequency component of this conductivity and my system is finite, so if L is finite, and I take eta to 0 before taking any thermodynamic limit, then I look at this function f, and I put frequency equal to 0. And what I see is that in the limit eta going to 0, this converges to some delta function. At the energy differences, E alpha minus E beta. And now if my system is as randomness, so this would give contribution only if I have some exact degeneracies between my eigenvalues. In random systems, don't have these degeneracies typically, so with probability 1, you never get in a finite system two eigenvalues which are exactly at the same value of energy. And therefore, what this means is that you will have a discrete spectrum, these eigenvalues will be spaced, and you will never be able to satisfy the delta function. So if you are in finite volumes, strictly speaking, you have no dissipation, which is related to what we said before. So you have a finite volume, you have a finite sum of frequencies, and this will give you dynamics which are quasi-periodic, and where you do still see this time reversal invariance, you have these revivals, so you do not have emerging dissipation in your system. So what you have to do to see a contribution to this dissipative conductivity is to take the thermodynamic limit before sending the regulator to 0. And this is how you can pick up contributions, because then if you take the limit, the thermodynamic limit, you will have accumulation of your levels. And by keeping eta finite, you are averaging over more than one levels, and therefore you contribution of these functions that remains finite afterwards when you send equal to 0 at the end of the calculation. And this obviously brings up two comments. So the first comment is that when you do numerics, it is hard to do this procedure. So, you have to take these two limits together, but you have not access to the thermodynamic limit, so you have to do scaling with two parameters, basically. You have to look at conductivity as it scales with both L and eta, and understand subtle features of this. And this is discussed in a paper that I put in the references, but I will maybe go back to this next time. So probing ETH or violation of ETH is much easier. if you do exact diagonalization, then controlling transport. And the second comment is that now I will conclude going back to the very first picture that I showed and to this comment of the fact that if I look, so let me first say something. So I said before that type of ergodicity breaking is not related to some symmetry breaking that you see in the partition function. But nevertheless, once you see this, you see that we are precisely in the same framework in which we probe symmetry breaking. So you have an infinitesimal symmetry breaking field that we are adding, which is eta. So I introduced it as just something to regularize my integration, but actually if you see, this is a little bit of imaginary part which somehow breaks the unitarity of my dynamics, and I keep it very small to regularize my integration, but then I send L to infinity, and that what I'm asking is that after this limit, if I send eta to 0, I still want to see some non-zero contribution to my dissipation. So eta is a field introducing a little bit of dissipation in your system. It breaks your unitarity, it breaks features of your dynamics that I talked about so far. And if you are in such a situation where you have dissipative transport, what is happening is that you put a little bit of this field and the system self-sustains this dissipation. A little bit like in easing, when you put a bit of field, you magnetize, you take the thermodynamic limit, and you have a finite magnetization, which remains even when you take the limit to 0. So the question here is, what is the symmetry? I think I said it already. So if you think about the picture at the beginning, so what I said is that you are localized, you look at your state at much larger time, and you kind of reconstruct what was your state at time t equal to 0. So this has to do precisely with time reversal symmetry. So the idea is that in generic system, when you have this emerging of thermodynamic transport, if you want, you effectively are breaking time reversal symmetry in this limit here. And in MBI, this mechanism doesn't work. So, and you probe this by looking at dissipative transport and seeing that the dissipative part of the conductivity is to 0. Okay, so I think I'm super late. Sorry.
Anyway, I mean, we are a bit late, but let us leave anyway time for a few questions already now.
I have to admit that I'm a bit confused by what you were saying about that thermalization does not happen in these systems. In the end, we are of course we are doing some random averaging, but in the end, we could also think about this. We'd simply take one realization of these of this random ensemble.
Yes.
And study these systems. If I understand you correctly, what you're saying is that almost all systems do not thermalize.
Yes, you mean almost all almost all realization of my randomness, if I take the randomness strong enough, are such that I do not thermalize.
Okay.
And this
but I mean, so this means if I take like any system and I have no idea about the system, I should expect that the system does not thermalize.
No, here I'm putting disorder.
I mean, so as long as the system is not So of course, if the system is like super fine-tuned, then it might thermalize. But if like there is some kind of disorder in the system, then the system won't thermalize.
So, okay, you're saying so when the mechanism which is behind this, okay, first of all, let me say, if you take a generic system with local interactions and no disorder, which is not integrable, you do thermalize. I mean, that works in general, in the sense that I kind of sketched before, and I will discuss more in detail on Thursday. Now, in here, you're adding this ingredient of disorder, and this really changes the situation, because you have potentials which do not have correlations in space. You're really throwing them independently from regions to regions of your lattice. And this is not the case of typical Hamiltonians without disorder. And this is what generates this phenomenology. Now, you can think that there are very special, I mean, if you sample your disorder distribution infinitely many times, there are, of course, very special realizations of your disorder, which are, as you said, fine-tuned, and they will give thermalization. But for typical, so with probability 1, for typical realizations of the disorder that you generate in an infinite system, this mechanism would not work, and you would see that, that you have what I've been talking about today. So perhaps you're saying that in the realm of disorder system, I should think about non-random Hamiltonian as a really special subset, which corresponds to fine-tuning the potential. And this is, in some sense, the case. So the deterministic potentials, you can think of them morally as being a super small subset of whatever Hamiltonian you can generate randomly.
But so in any realistic system, I can never fully describe them by the like these Hamiltonians that we usually write down, because they are not as clean as we always would
right,
like.
But to get
there's
this,
always some disorder.
Absolutely, but to get this, you need strong disorder. So you can think, okay, my realistic systems will have some impurities that I cannot control, and therefore I could model them introducing fluctuations. But if these are weak with respect to the rest of the energy scales in your system, then you wouldn't see this. So here, as I will try to explain next time, you really need that you have large fluctuations of these local potentials. Large energy differences in the local potential if I look at the system here and if I look at the system there. And if you just add small impurities, in general, this is not the case.
Okay, so this is something which does not happen too often in nature, but it's rather something that we have to create artificially.
I mean, if you have a system where you have fluctuations, but the energy scales of these fluctuations is negligible with respect to the other energy scales in your system, like the interaction strength or the kinetic energy, then you are in a weak disorder regime, and there you do not see MBL.
Okay, I see. Thank you.
Thanks for the question.
Other questions? If not, let us stop here because it is late, and we reconvene at 2 p.m. for the lecture of Karelian Scoutons. And remember that there will be a discussion session tomorrow afternoon anyway, to ask further questions to Valentina and to Karelian and to Nigel. Okay, goodbye.